right, so today we have Sid Sheth, founder and CEO of D-Matrix, which you can find at d-matrix.ai. Tagline is redefining performance and efficiency for AI inference at scale. And with that, Sid, welcome to the podcast.
Thank you, Ben. Thank you for having me.
So our topic today will be hardware for AI, particularly hardware for inference. And Sid, I have a litmus test for people I talk to in hardware. I first go to their LinkedIn page and see have they actually built chips before.
Yep.
Because there was a wave of chip startups, and it turns out that a lot of the people were not chip industry veterans, and
Yeah.
it turns out hardware is not like software. You have to build a few chips and maybe fail at a few before you know what you're doing. So
You're absolutely right.
so with that's my way of providing our audience with your background, which they can look up on LinkedIn. All right. So inference hardware. So first of all, I guess around 2017, 18, there was a wave of hardware startups or focus on training.
Yep.
I think the only one really of significance left is Cerebrus, who I know well. I'm friendly with them. But now it seems like more and more people are targeting inference. And it makes sense because
Yeah.
people are using all these foundation models. Every time you use that, that's inference. So I guess, Sid, at a high level, I noticed, for example, that you folks focus on memory, or memory is one of the things that you guys highlight. So
Yeah.
before we go into what specifically you folks do, which you call, I guess, digital in-memory compute, I think is the term you use. So for our audience who might be familiar with things like SRAM or high bandwidth memory,
Yeah.
can you talk us through what SRAM and HBM are great at and what they seem to be lacking at when it comes to inference?
Yeah. Yeah. No, thanks for that introduction. And you're absolutely right, Ben. If you're going to build an AI chip company, the litmus test is how many chips have you built to earn the right to build an AI chip company, right? And my just a side comment. I think you need to have built and lived through a cycle of at least three in your career.
Yes. Yeah.
At least three. I've done 15 plus, right, in my career. And
And built means beyond tape out, right?
beyond tape out to production,
Yeah.
and beyond production to deployment, right? Absolutely, I think the first one is where you learn. The second one is where you take a important role in running the chip development, and you will probably fail. And the third time is when you do the same thing again and you succeed, right? So if you're a quick learner, you probably need three. If you're not a very quick learner, somebody like me maybe needs 15 plus, but but you need to have done quite a few of these to really get this figured out, right? And so the team here at D-Matrix, obviously very experienced, has done a lot of tape outs, a lot of chip development. We are very good at that. And when we started the company in 2019, we were not in that first wave of AI chip companies, as you said, right? We were kind of second in the second wave, pre-ChatGPT. But there was enough companies doing what we called edge inference. There was enough companies doing training. There was enough data that we could learn from. And we decided that it doesn't make sense to build yet another edge inference company that is going to be focused on computer vision, with lots of computer vision companies at the time. Most of them didn't go anywhere. And then it doesn't make sense to do training because NVIDIA was the 800-pound gorilla in training. So we focused on cloud inference specifically because we didn't see a dedicated solution for inference in the cloud or in the data center. And
This was pre-ChatGPT.
Yeah, this is 2019.
So it's kind of counterintuitive at that point.
Very counterintuitive, very counterintuitive. In fact, I like to tell the story about how many investor meetings I had where I would just have to explain to them what inference was. So what is inference and why is it important? And why is it important in the data center? And why do you think D-Matrix will have a role to play in the future? And of course, all of that became a lot easier post ChatGPT, right? But I think back then we just went to the to first principles and really tried to understand what the inference computing workload was all about. And what we realized was it is a lot of parallel compute, repetitive parallel compute, trying to access a lot of memory because all the data is sitting in memory. And if the workloads keep getting bigger, you know, there would obviously come a time when you need to access that memory very, very often. So very, very intuitive, very, very simplistic approach to what, inference would look like in the future. And so we went about building a solution that was built around memory and compute integration. So how do we put memory and compute as close together as possible?
But what about the whole point that there's SRAM and HBM? What did
Yeah, yeah. So once we decided that we wanted to put memory and compute together, then the next question to answer was what type of memory should we put together? And obviously HBM doesn't lend itself very well to compute integration, at least not back then, because it's a very power hungry memory, it's a costly memory. Any attempt to put compute and HBM together, would be very difficult because compute, you won't have the requisite amount of compute that you can put alongside that HBM because of power and energy constraints and cost constraints. So we essentially went down the path of SRAM inference as a first step. We said, you know what, we are just going to try to pack as much SRAM as we can close to compute. We created this new type of compute.
but this was Sid, as you described, this was before ChatGPT, so the models were like computer vision models that were not as ginormous as.
They were not as well, I know again, this is circa 2020, call it, right?
Yeah.
When we were trying to make these decisions. And GPT-3 was just round the corner and just coming out. The largest model was around 175 billion, right? GPT-3 was 175 billion parameter model, the largest variant. So the models were approaching, 200 billion in size by then, right? So we knew, and the trajectory was, people were, extrapolating what, these models would look like in the future, and they were just going up in trajectory, right? So we knew that the models were getting larger, so we had to do
But
something.
still, from a commercial point of view, GPT-3, it's not like there were a lot of users.
There was not a lot of users. There was not a lot of users,
Yeah,
but I think the capability was becoming clear to us.
yeah,
I think
yeah.
we were pretty, what was very promising was like, wow, these models are very capable. They can, the first signs of life were visible in in GPT-3. GPT-3 was when the first signs of life were visible. What's possible with transformer models? BERT models, by the way, the BERT model that Google had invented and written about was already deployed in 2020. They were using it in Google language, English language search. They were planning to use it in foreign language search and whatnot. So I think the use cases for transformer models was there. They were quite versatile. We were getting feedback from a lot of the hyperscalers. These are very versatile models. They're not just limited to text. In the future, we expect them to be multimodal and that the size is increasing, right? And so
Yeah, yeah.
people
And then around that time, people were already doing embeddings, right?
they were doing embeddings, yes, yes.
Yeah,
Embeddings had become quite popular with the recommender systems, right?
yeah, yeah.
So that same concept was being carried into the transformer models, and how do we vectorize, multimodal data so that the transformer models can understand it, right? All of that was happening right around that time, right? So as a company, we just made a bet. We said we're going to go focus on transformer acceleration. The hardware is built to support all different
So
types of,
like you said, you started out, let's look at SRAM.
yeah.
Yeah.
And SRAM was the first memory technology we adopted. We said, you know what, we're going to find a way to integrate compute and SRAM. And we today our first product is essentially an SRAM inference accelerator, which has got 10 times more memory than any other solution on the market, right? And so we can accommodate bigger models. So factoring in that data on bigger models that we just talked about, how models were getting bigger, we tried to pack as much SRAM into the platform as we could. And so today we have about 10 times that capacity of SRAM, right? So that's really was the first step we took. And it's been a good intercept for the market because the market is now just moving to fast inference, low latency, what they call low latency compute. And this SRAM-based inferencing solutions are now becoming very popular.
And then actually, before we go into what you're doing,
Yeah.
I think some of these early players like Grok and Cerebrus, right? So they also relied on SRAM, but
Hmm.
then they eventually had to add external memory, correct? Because
Hmm.
the LLMs grew too large to fit on a chip,
That's right. That's
right?
right. Yeah.
So everyone was kind of realizing that memory was going to be a key bottleneck. People talk about Moore's law, but what about memory?
That's right. That's right. Exactly. Exactly. I mean, that was the.
Yeah.
I mean, I think for anyone looking at the data, it was pretty obvious, right? Because the models were getting so big so fast that trying to outgame the model size increase by thinking that you can pack more memory in a single chip was just not going to work. Anybody who tried that failed, right? Everyone needed some sort of external memory to make the solution work. We kind of embraced it early on. So we have a second tier of memory with LPDDR where we can accommodate, there's like close to, we can do 256 gigs on a single card, close to like, 10 terabytes in a single rack, right? So we always have that second tier of memory that we can spill over into to accommodate these extremely large models or large context. I mean, don't forget the large context sizes for these models, right? So between the large context sizes and the large models, the KV cache sizes are just exploding, right? And to accommodate these extremely large KV caches, you need all that memory. So we have that capability in our solution.
So when you folks started, right? So this was before, like you said, before ChatGPT, right? So and of course, fast forward to today,
Mm-hmm.
right? So now most of the usage for AI is these foundation models. Many of them are text based,
Yeah.
and you have this kind of I guess like a two-stage process, right? So you have prefill and decode.
Yep.
Uh, so that preceded your company, right?
That preceded the company, absolutely. Because what happened is, again, let's take a step back, right? If you look at the evolution of the transformer model, the first wave of transformer models were not generative, right? They were strictly representational, as they call quote unquote representational. They were very good with data and understanding data and predicting, next, I mean, completing sentences based on, the data that they've been trained on, right? But they could not predict it could not generate content or predict the next word based on content that it had never seen before, right? So when the generative transformers came, and those came in, call it 2021, 22, GPT-3 was the first generative transformer. They had this behavior where what we just talked about, the KV cache, you store all the context, and then you kind of essentially every time you generate a new token, you look at that context, and the model is capable where it can generate the next best token based on all that KV cache data that it is seeing, right? So suddenly models could actually generate content based on queries that it had never seen before or data that it had never seen before, right? So that was a new behavior, and that is what led to the prefill decode, right? So basically, you have let me give you an analogy that will help the audience, understand a little better. It's like, when I ask you a tough question, right, Ben, or you ask me, you're the one asking me the question, so maybe you ask me a tough question, right? What I have to do is at least spend a few seconds thinking about it, right? And then I process your question, and then I turn around and answer it, right? So the thinking process is prefill, right? That's me pre-filling my brain and memory with your question, understanding what you are looking for, and then turning around and starting to speak the answer, which is the decode phase. Decode is where I'm beginning to speak the words, right? So prefill is I'm thinking, decode is I'm speaking, right? And so that's very similar to what the generative AI models do today. You give them a tough, a kind of a very abstract question or a question that requires a lot of thinking. First thing it does is prefill, which is it just generates all the context as thinking, and then the decode is when it starts spewing out the tokens, it's speaking, right? And the decode part is very memory intensive because it needs to access all that KV cache data. The prefill part is very compute intensive because it's all it's doing is thinking and processing, right? So the first part is compute, the second part is memory. And and again, when you talk about memory, you when you want to speak, when you're ready to respond, you want to respond quickly. You don't want to respond very slowly, right? If you ask me a question and if I'm going to respond with, a 2 second gap between each word, you're not going to enjoy my response, or your audience is not going to enjoy my response. So you want to speak the response very quickly. So latency begins to matter a lot when you are decoding and speaking. And that is where a memory bound or a memory friendly architecture or a memory centric architecture like the one that we have built is extremely well suited. So SRAM based inference today going to, we'll talk about how we are migrating to DRAM based inference. All these architectures that are memory centric do extremely well in that second phase, the decode phase, where you're meant to kind of respond quickly.
So Sid, for our listeners who are not steep in hardware, right? So
Mhm.
they might hear the term HBM, high bandwidth memory. So
Yeah.
explain at a high level what that is and why uh, it, in your mind at least, it doesn't seem to be optimal for inference.
Right. So HBM, just from a strictly from a historical perspective, is a memory technology that was invented, call it in the mid 2010s, right? So it has been around for some time. It is a DRAM based memory. So it's, under the hood, HBM uses the same DRAM technology, right? A similar DRAM technology. And then what it was very good at was what was missing in the older DRAM technology was the bandwidth was, if a processor needed to access memory with a very high bandwidth connection, that was missing in the old DRAM technology. It was just a very thin pipe that went between the processing engine and the memory itself. So HBM set out to solve that problem, right? So they essentially created this new interface between the compute and the memory. There is it's a very, another analogy here would be it's a highway with a lot of lanes in it, right? Lots of parallel lanes. So instead you go from a 1 lane highway to a 16 lane highway. Each of those highway lanes can run at 80 miles an hour, call it. So now suddenly you have a lot more bandwidth, right? You have a lot more throughput and bandwidth. So that is what HBM solved for. It was a entirely new interface to the processor so that it could get access to lots of data very quickly.
And historically, Sid, mainly training, right?
And then it was really targeted for high performance computing initially.
Okay.
And the training workload just happened to emerge right around that time. Like 2016, 2017 is when training workload started getting really large and they needed access to lots of data. And you want to run those training jobs very quickly, right? And accessing lots of data quickly became important. And training is essentially a high performance computing workload effectively. So the HBM memory found itself a nice home. It was a perfectly well suited technology for the application that came around at that time, and it became immensely popular with NVIDIA GPUs. So NVIDIA GPUs essentially fitted. The older NVIDIA GPUs did not have HBM. Pre 2015, NVIDIA GPUs did not have HBM, right? So then they retrofitted the GPUs with HBM, and that is what has become the predominant training solution of today is the GPUs co-packaged with HBM memory.
And then for inference, the
Mhm.
reason it's not ideal is
Well, inference is, kind of a diametrically opposite problem, right? It's all about efficiency. And when we talk about efficiency, we are talking about efficiency in cost, efficiency in energy, efficiency in time, right? So if you look at the three most precious resources known to humankind, it is really money, time, and energy, right? These are the three most precious resources.
not in that order,
Not in
audience.
that order, not in that order, not in that order. Every person has a different priority, but I'm just listing out the three that people mostly think about on a daily basis, right? And you look at HBM, it's very costly, right? Very energy hungry, right?
So
And
so wait, stop. So
yeah,
costly,
very costly.
can that change with economies of scale?
It
Energy,
Yeah, energy.
maybe is that a solvable problem?
Right. And so we'll talk about that. And then the third one is it just does not have enough bandwidth anymore
Yeah.
for the AI application. So it's not very fast anymore. It used to be fast for certain app, but not fast anymore, right? You need faster and it's not faster anymore. So again, when it comes to speed, cost, and energy, HBM is not able to keep up, right? It's just not able to keep up. And
So
it's a
so is that are those three things solvable, or there's something fundamental that just prevents HBM from becoming viable for inference?
I think if the technology innovation on HBM had matured to a point where it was just about volume economics, then it would have solved the cost problem. But with the pace of AI workloads and the need for innovation, there is constantly new innovation happening, even with
And then the speed, can that be innovated?
the speed. Again, there's it's physics, right?
Okay.
There's only, there is limitations on how many lanes you can put on the highway, right? I mean, yeah, you want to go from 16 lanes, you can't go to 1,000 lane highway, right? Overnight, you go from 16 to 32, then you go from 32 to 64. You take those steps. So I think there is incremental steps you take. So again, but that is not enough. It's not enough anymore. You need to go to the 1,000 lane highway very quickly, and HBM won't get you there in the window when it needs to get there, right? So I think these are, some of them are just, physics problems. Some of them are, there is so much innovation going on that the cost curve just does not come down that quickly, right? And the rest is, uh, the AI applications are just running way ahead of the speed that the HBM memory technology can offer, right? So on all fronts, HBM is no longer keeping pace with what the industry needs.
But for training, it's still viable.
For training, it is very viable and will continue to be viable, will continue to be the memory technology of choice for the foreseeable future. So I think HBM has a very bright future on the training side. Even on the inferencing side, for certain extremely high-end applications, HBM technology is probably okay as a starter. But I think as the applications proliferate, lots of users come online, you care about speed and cost when, economies of scale become very, very important. And that's when HBM will not be able to serve the needs of inference.
Which brings us to digital in-memory compute.
Mhm.
It, is it just a marketing term?
A little bit of both, right?
Explain to us at a high level what it is.
Yeah, it is a little bit of both. So I think in-memory compute, the reason we called it in-memory compute is because we essentially created a fabric of compute and memory. We took an SRAM, SRAM memory cell, and this might get a little technical. Hopefully your audience appreciates it. But traditional SRAM memory cell is, call it has 6 transistors inside that memory cell, and it stores 1 bit of information, right? But it's only a store-only cell. It can only store data, right? And you can read the data, write data, but it stores data, right? And it can store 1 bit, and that's 6 transistors. Now, what we did was we took that cell and we augmented it with a few more transistors and gave it the ability to do multiplication. So it could do, very rudimentary compute, right? And store. So it can now store and compute in the same cell. And it's a 10 transistor cell, right? So basically, suddenly you went from the 6 transistor cell to a 10 transistor cell, but the 10 transistor cell could store data. It could store a bit of information, but it could also do multiplication on a single bit, right? Then
But uh, I guess user experience, it feels like SRAM.
it is like an SRAM, exactly. I
Yeah.
mean, it is basically from to the outside world, they're addressing a traditional SRAM, right? So
So
you have
all the goodies and benefits of SRAM you get.
or more, even more. So traditional SRAM, if you look at the traditional SRAM memory hierarchy, the way you read an SRAM is you can access one row in that SRAM at any given time, right? That is how it works. In our case, we built it like a data flow engine. Basically, all the rows of the SRAM can be accessed simultaneously. So as the data is coming in, as data comes into that memory, we activate all the rows of the SRAM simultaneously. So our throughput is a lot better than a traditional SRAM, right? That was specifically done because to improve the speed and throughput.
So mapping this to what we talked about earlier, which is this two-stage process of prefill and decode,
Yeah.
how does DIMC benefit and manifest?
That's right. That's right. That's the key thing, right? What benefit is it to the user? So I think what happens is now because the matrix math, because matrix math is what? Multiplication and addition, right? It's a Mac unit, multiply, accumulate, right? And
So hopefully the models don't change and we still have the basic matrix operations in the end. Otherwise, the
yeah,
hardware will need to change.
then the hardware would need to change, but then lots of, pretty much every chip in the industry will need to change, right?
Yeah, yeah,
Right. I think not just us.
yeah.
And matrix math has been, around for, decades, right? And so to find something new will take some time.
Yeah.
If a new computing paradigm were
Or
to
new architecture that's not transformer based, I guess is what
new
I'm.
architecture, even if it is not transformer based, even if you have other, they still use matrix math.
Yeah, yeah,
I
yeah.
mean,
But
yeah.
hopefully they don't involve more than matrix multiplication, right? So,
And I would so let's while you're on that topic, Ben, let's break it down, right? So
yeah.
today's AI models, transformer, non-transformer, there's matrix math, there is non-matrix math also. So there's linear
Hmm.
algebra, there
Yeah,
is what they call non-linear, functions that are embedded
yeah.
inside those AI models. Transformers specifically have, there's a lot of vector math, there is matrix math, there is also basic operations like reshapes, you're reshaping matrices.
And all these AI chips are optimized for all these
That's right. That's
computations.
right. So our chip included, we are
Yeah.
optimized for matrix math, vector math.
Anyway, I derailed us from the prefill and
That's
decode.
right. That's right.
Uh,
And we'll bring it back to that.
yeah,
We'll bring it back
yeah,
to that. So just so for your audience, so that they understand, all AI models are not just matrix math, they're more than
yeah,
matrix math,
yeah.
right? And the matrix engine that we built with the DIMC is just one type of matrix math engine, but it's a very, very efficient matrix math engine. And why it becomes efficient is because of what I stated earlier. The compute and the matrix math is happening inside the memory. So you can store the model parameters in that memory, and the matrix math is happening right there without having to move the model parameters around. So when you don't have to move the model parameters, you save a lot of time, you save a lot of energy, right? And obviously it leads to cost savings, right? So going back to those three most precious resources, money, cost, and time, we just made a big leap by putting the model parameters in a place where they don't have to be moved around, right? And so suddenly you save time, you save energy, and in and over time you save cost, right? So we have made a big difference to those three key metrics that are very, very important for inference. And whether it is prefill or it is decode, when it comes to decode, you just want to save a lot of time becomes extremely important, right? Because you want to spit out those tokens very quickly. That's where a digital in-memory computing engine that does not have to move the data around and you can compute in place, you save a ton of time and energy, which is where it comes really, really handy. It comes in really, really handy during the decode phase, where you are essentially trying to generate a response very quickly with the least amount of energy spent.
And this is like you said at the beginning, this is a data center chip,
Yeah.
right? So in a single rack, how big is the DIMC?
So we have, just to give an idea, so we'll go from the DIMC is like a Lego block, right?
Yeah,
Let's call that a Lego block. Then we piece all these different
yeah.
Lego blocks and we build a structure. So within a single card, single PCIe card, that is our unit, product shipment today. We have 2048 DIMC Lego blocks inside one card, and there is 64 of those cards inside a rack, right? So you can do the math. I'm not very good at math, so 64 times 2048, whatever the number turns out to be, is the number of DIMC engines.
And so for our audience who want to map this to model parameters or model size,
Yeah.
how big are the models that are running?
Right. So now again, going back to, there's two tiers of memory. There's the DIMC tier, call it, right, which is the SRAM tier. If you want to run out of the SRAM tier, we can run models that are 100 billion parameters in a single rack, right? That is anywhere between 5 to 10 times better than anything on the market today.
And so the types of models that run are the types of models that we have today, which could be multimodal, which could be reasoning.
Absolutely.
Yeah.
Absolutely. I mean, we don't discriminate on, model type, right? I
And
mean,
then for reasoning models,
mhm.
I imagine the user experience just improves so much, right?
Oh, absolutely. Because see, reasoning models now, what the model has to do is do a lot of thinking internally. It is actually generating a lot of internal tokens, right?
Yeah.
It is essentially it processes a question, then it does a lot of internal thinking where generates internal tokens, and then it starts generating a response. So you want to shrink that latency period. From the time you pose a question to the time the response is generated, you want to reduce the amount of time. So latency again becomes very important. Again, an architecture like an SRAM architecture, DIMC architecture is extremely useful for those type of reasoning models.
So usually there's a trade-off, right? So low latency, meaning answer me quickly,
Yeah,
or high throughput, or answer 1,000 users quickly.
right.
So is there a trade-off?
There is absolutely a trade-off, and we are very good at the latency part, right? So we are not, if you want thousands of users and you want extremely high throughput, actually the GPU is a great solution for that application, right? We are not really going after a high throughput application. That is not where we play. We are playing in the what we call the medium throughput, low latency, right? So there's a trade-off. If the throughput is very high, the latency is going to suffer, right? Because you are processing all these different users. That means you have to spend a lot more time doing that. That
So,
means
so, so wait, so I shouldn't believe the people who say there's no trade-off in their chips?
no, you should not. Those are probably the guys who haven't designed too many chips in their life, you know. So I think, look, the trade-off is always there. There's no free lunches when you're building chips, right? So if you're servicing a very high throughput application, you're going to pay in terms of latency. If you're servicing an extremely low latency application, that means you can't serve a lot of throughput, right? And you can do medium throughput. In our case, we have come up with a memory hierarchy that allows us to serve medium throughput, but we certainly cannot go after the extremely high batched throughput type of applications. That is not really not what we are targeting anyway.
So, one of the things that I think more and more people are beginning to understand about hardware and AR hardware in particular
Yeah,
is there's hardware, but there's the software stack, right? So
correct.
NVIDIA
Yeah. Hmm.
famously
Yeah,
has
yeah,
CUDA, and then now AMD is trying to improve ROCm,
yeah.
and then there's open source initiatives like Triton. So
Yep.
if I consider using your hardware, how do I know my models will run on your hardware?
Yes, yes. No, that's always a great question. So I think first of all, let's break down training and inference, right? So training software stack, inference software stack, there is some differences there. Training software stack, I think, obviously NVIDIA has done a phenomenal job of building
Years
out
and
for
billions
years, for
and
years. And
billions in
look, it's
investment.
not it took them years to build out that capability and all the different libraries and more importantly, the programming model, right? The programming model for that hardware over many, many years. And
Yeah,
then
CUDA preceded deep learning.
CUDA preceded deep learning. And,
Yeah,
if you read, the book that just came out, NVIDIA Way, they talk about, they spent almost 10 years as a company just building out that programming model, training people in universities and
yeah,
research institutions. So, this was a long journey for them,
yeah.
a lot of pain and investment that went into it. So they absolutely deserve all the success that they are getting, with that, right? It took them years and years, right? Now on the inferencing side, it's a little different, right? I mean, on the inferencing side, it's not so much about training a model, having different possibilities that you want to experiment with. You want to program the hardware with different approaches so that you can exploit different capabilities in the models. All that is not, the model is already trained, right? The model already has certain capabilities. All you want to do is run it efficiently, right? And for that, typically you are taking a model, and what happens is you need low-level kernels that will take that model and map it to the hardware, right? And so it really comes down to the kernel library, right? Now again, here NVIDIA has a huge advantage because NVIDIA has been building that kernel library for years, right? So their coverage in that kernel library is a lot broader, right? They can cover many different models. That's why the argument, right? Oh, if I have a model and I want to run it seamlessly, most likely it'll run seamlessly on an NVIDIA GPU, right? Because the model library already has the coverage, right?
And most of the people building the models and trying to run it for the first time probably default to that.
They default to that, and it works seamlessly, right? I mean, for
Yeah,
if your goal is like, look, I just want a model to run on some hardware,
yeah.
right? I don't really care about extracting performance and cost and
Yeah,
all
because
that.
I can be a researcher and I'm not sure yet if this is going to get deployed to
That's
production.
right. That's exactly right. So you're just trying to on ramp. You're just trying to on ramp, your work. You have something you want to do and you want to on ramp that work. I think the GPU is the best solution, right? It'll allow you to on ramp very quickly. You will figure out you'll be able to do a lot of experimentation very fast. Then eventually, say you get to an answer, right? You say, okay, now I think I know what I want to do, but now I want to optimize it, right? And I really need to optimize for that again. Back to those three things: optimize for cost. I want to optimize for energy. I want to optimize for speed. that is what my application needs. That's where a solution like ours can come in very handy. So the portability becomes very important. How quickly can I take a model that was built to run on a GPU? How quickly can I quickly port it to the D-matrix solution, right? And so that is what we are focused on, and that is where we work with a subset of models, or we, in some cases, we open up our uh, kernel library. We essentially give our customers the ability to write kernels for our hardware, right?
So,
And that is what allows them to port
so
models.
I guess, Sid, let's give the audience a sense, particularly because of this issue of will my model will my models run on D-matrix hardware, right? So I don't know how comfortable you are, but who are some of the users of D-matrix, for example?
Yeah, yeah. So I think in our case, our users are, we realized very quickly that if you are going after a broad community of users, it's very tough to beat NVIDIA because NVIDIA has been there for years, right? I mean, they've already built up a very broad community, and, yes, you can make good progress there, but you can never catch up, right? If that is, it takes years and years to catch up. So certainly at the right time, we will do that. But I think what is more important to us right now is finding the right applications that can run on our solution that can give the users a real meaningful benefit, right? And there are many of these applications that care about extremely low latency, that care about
And
speed.
so right now the typical D-matrix user runs on-prem.
They run, could be in the cloud also. So I think, there are a few applications in the cloud, but you're absolutely right. I think most of them are on-prem solutions at hyperscalers. In some cases, like sovereigns and neo clouds, we are in the cloud, right? So basically, what they do is they come and tell us, oh, we have a subset of these 20 or 30 models that we think are best suited for your hardware, right? So why don't you take those 20 or 30 models and port it onto your hardware? And then we'll just run those 20 or 30 models, right?
And what is so is that still a painful process, the porting?
Not these days, because what has happened is, if you look at the
Because there's only a
kernel,
few, there's a lot of shared components in this architecture.
exactly, the transformer architecture is, the fundamental to all these models. So, you have attention layers, and, you have, I mean, they're all beginning to look more or less the
But
same.
this is still a step that you have to do, not the customer.
That's right. In these engagements, this is the step we would have to do, where we would essentially take that list of models that the customer wants and write up the kernel libraries for those models and give it to those customers, right? And then they can run those 20 or 30 models on our hardware. And the most popular models these days are, the open source models, whether it's Qwen, DeepSeek, Kimi. It's a list of, less than 5 or 10, right? That are really, really
But
popular.
then the customer may have fine-tuned the models, right? So,
You may want to fine tune it, and we can certainly have the ability, we can either give them the ability to do that, or we would do it for them, right? In most cases, we have already optimized these models heavily before we give it to them, so they may not even want to really fine tune it too much, right? So that is one class of user. The other class of user is somebody who says, no, guess what, D-Matrix, I don't want to share the model with is my model. I have the sophistication to port that model onto your hardware. So just give me the ability to write kernels. I want to write the kernels. You don't write the kernels. I'll write it, and I will port that model onto your hardware. So this is typically a hyperscaler that has proprietary models that they want to port onto our hardware. So there's two classes of users, right? And we support both.
and I guess on the enterprise side, so you have to have a certain scale of usage in order to even go down this path, right? So,
And they do, right? I mean, if you look at all the neo clouds or the sovereigns that we work with, they have a certain scale. They already have a certain scale, or at least they're planning to deploy at a certain scale. So absolutely, I think I don't think it's a scale issue at this point. Anybody who wants to be a real player in this space has to deploy at scale, right? So that is.
no, but I mean, so your customers tend to be the providers, it sounds like neoclouds, hyperscalers, not enterprise.
Not well, we talk to enterprises, but most of the enterprises still host, their applications in the cloud, right? So
Right.
they need us to go. They would ask us to. The first question they ask us, oh, I have this application. Oh, I love it. Supposing I have a video application or an image application or a code application. Oh, guess what, D-Matrix, I really think your hardware is very well suited for my application, but who's going to host it? Right. And so then the next question they ask us is, do you have your preferred partner that I can go work with to host my application there, right? They don't want to host it yet. Most of these companies are still not hosting their own applications. If you look at the Fortune,
But they're at the point where, okay, so we validated this, we've deployed it, and now it's about latency.
latency, its cost, it's I'm spending too much on I'm deploying it in a region where energy is very costly, so I want energy efficiency, right? It could be different constraints.
Yeah, interesting. So, um, why not set up your own cloud?
That question comes to us quite often, and we just feel it is not necessary, right? Our hardware was always built in a way that we can sell it to or partner with various cloud providers who can very easily build a cloud offering with our solution, right? It was built from the grounds up to fit inside, servers from various providers, whether it is, somebody like today we have a partnership with Supermicro, but in the future we could work with various other server providers, AI server providers. There's nothing that we built here that requires us building our own servers and our own racks, right? We built our hardware in a way that it can be packaged up by various different AI server providers, and they can go build their own racks and deploy those racks, right? So we have a more collaborative approach. Let's go work with the ecosystem. Let's leverage the ecosystem. I mean, people have been building servers and racks for decades. I mean, why do we need to go build that ourselves unless the building of a server or the building of a rack meaningfully augments the advantage that we bring, right? And in our case, all our advantages in the software and the silicon and the cards. So the way we package that up into a server and a rack can be done by many, many partners that we work with, and let them go work with all the different cloud providers. We don't need to be a cloud ourselves for that.
Cerebrus did it.
They did it. I mean, that's a question for them. They
Yeah.
probably, is there a set of constraints in the way they build their hardware that forces them down that path, right? I'm not sure, but I
Yeah,
think that,
because they're hard, that big
yeah,
wafer-sized chip, right? So
sure,
it's
yeah.
very specialized uh, kind of setup, right? Cooling system and all of that.
Right,
That
right.
they probably decided we can do this ourselves and host it ourselves, right? So
That's
your solution seems to be much more pluggable into
plug and play. That
standard
was a deliberate choice,
for
yeah.
you. Uh,
Yep,
yeah,
yep.
yeah.
We wanted to make our solution available to a broad ecosystem, right? The only way to make it available to a broad ecosystem is to collaborate with the ecosystem, and that's what we did. So our go-to market is very different, in that sense.
And what is so looking ahead, so what are some of the things that people should pay attention to in this area of inference and production AI?
Well, inference, I think we just entered the age of inference, right? I think so. Inference is now, everyone is talking about it, everyone wants access to it. And I think the whole discussion and narrative now is about how to make it usable. How does inference, um, become available to the lay person, right? Who comes into work every day and, you are
And
working
it'll be more
on
compute intensive with multimodality, right? So right now, a lot
multimodality.
of the inference that people do is just chat,
That's
text,
right. That's right.
right?
So
So
multimodality is one thing, but I think I was referring more to agentic and how to
yeah.
make the workflows. Like when you come into work, you're dealing with all the different office tools, and somebody else might be dealing with CRM tools and ERP tools and whatnot. And then how do you truly have a agentic layer on top of that, which is all AI driven, that can basically take the data from all these different tools and make meaningful decisions for the user, right? And improve productivity that way, right? As opposed to the user having to kind of work through the different silos and gather all the data and make decisions themselves. So I think there is this whole enterprise use case around agentic, which I think we are very excited about. I think that is where a lot of the value creation will happen. And of course, then there's the consumer use case, which is what you just referred to, people just chatting or generating, videos and, generating, images. And is that leading to a lot of slop on social media?
Well,
Probably is, right?
video generation would be very compute intensive
Very, very compute
if it
intensive.
becomes widespread, right?
It will be widespread. I
Yeah.
mean, it's not a question of if, it's a question of when.
Yeah.
It'll 100% be very widespread. And look, I think there's lots of amazing applications that can be unleashed when video generation becomes truly interactive, right? I mean, where you can interact with the AI tool, just as you are interacting with text today. right? It is not an offline experience. Today, video generation is an offline experience. But imagine if it became truly interactive. Again, that is an application or solution like ours could unleash because of the, again, it's back to memory bandwidth, and having all that additional bandwidth for interactivity. We have that. So we could, at some point in the future, unleash a true interactive video generation application.
So Sid, what about on laptops, right? So the analogy so what I'm about to say, I guess is inspired by what happened to what we have on our laptops, right? So what about high bandwidth flash, right? So
Mm-hmm.
where you might have 10x, 20x more memory capacity.
Mm-hmm.
Um, kind of what are people working on that kind of
It's
problem?
promising. It's a
Yeah.
promising technology for client applications, right? For sure, right? Where all you want to do is run a lot of inference very quickly,
Yeah.
right? So once the model is downloaded into the flash memory, the thing with flash memory is it's not super programmable, right? So very difficult to use it in a data center type of application. There might be some use cases in data center where you're constantly programming the memory. But in a client application where it's like, oh, the model is already downloaded, all I want to do is use it, repeatedly, and but I want more capacity, and I wanted, I wanted, cost-effective memory technology, right? SRAM is not a good choice there. HBM is not a good choice there, right? Because SRAM won't give you the capacity, plus it's very expensive. HBM is, too power hungry for a client application, and also very expensive. So that's where a high bandwidth flash type application could be very, 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 very useful, right? And that is why people are exploring that.
Yeah, yeah, because there's definitely like a memory wall gap, right? So the flops are growing much faster than memory speed.
That's right. That's right. And that
And
is
so
exactly,
is that gonna be a problem moving forward?
it is a problem. I mean, it is a
Yeah.
problem. It was a
Now,
problem.
yeah, yeah.
It was a
But I
problem.
mean, even
Yeah.
more pronounced.
It has, yeah, that has been a problem for the last 30 years, right? And
Yeah.
it has just become very pronounced because of AI. AI has just, put a huge lens on that memory wall problem, and that's exactly what D-Matrix set out to solve is kind of break through that memory wall, or at least collapse the memory wall with our approach, right?
So you still haven't named the customer.
Stay tuned. Stay tuned.
Okay, okay.
We'll,
So
yeah.
we just want to make sure it's real and not vaporware.
Yeah, absolutely. No, no. I think it's you're welcome to our labs, and we'll show you the hardware running here and even in our customers' locations. But yes, we are just coming onto the scene. The company just announced the product a year ago, and now this year is when you'll start hearing more about the product and customer announcements.
So is there additional juice that can be squeezed out with innovations around interconnects and maybe revisiting, uh, I guess, topologies and how these models communicate and move around?
So I'm assuming you're referring to how to scale up and scale out
Yeah,
the compute, right? And so yeah, no, there's a whole different topic, right? We could talk about for another hour,
yeah.
but there is a lot of a
And
lot
that's
of
do these things matter in inference?
oh, absolutely.
Yeah.
I think they do because models again are becoming big, right? And if you want to, even when we talked about a rack level solution, right? You need scale up for that rack level solution, right? How do you connect the servers to each other, right? Like today, we connect the cards inside a server over PCIe, right? So there's a PCIe fabric inside the server that connects the cards to each other. But then how do you connect the servers to each other inside a rack? So there you need a scale up network. So we have our own solution today. It's called Jetstream. It's an Ethernet based networking scale up solution. This allows us to connect multiple servers together inside a rack. All right. But the ecosystem is migrating. I mean, NVIDIA has NVLink, which everybody has heard of.
Yeah.
And then Broadcom has announced recently something called ESUN, Ethernet Scale Up Network, ESUN, ESUN. And that is going to be the scale up network from the Broadcom ecosystem, right? It's all Ethernet based, right? And then there is UAL, that is another ecosystem that is emerging around scale up. So there is multiple choices that are emerging for scale up and how to connect. And that is really the next big opportunity, how to connect all these servers within a rack and over time, how do we connect multiple racks to each other, right? There's obviously InfiniBand, which was very popular, right? There is Ethernet today. Some people use PCIe actually for scale up, right? So there's various options, and you can break down, and there's pros and cons to every option. But I think over time, my feeling is NVLink is here to stay. That's because it's NVIDIA. There's Ethernet for everyone else, which is going to be eSUN, and you'll probably have some deployments of Ultra Accelerator Link, which is UAL. That is going to be the third option. But I think my sense is NVLink and eSUN will dominate the landscape.
And in closing, so the hardware space seems to be more fragmented, and there's less talk about open standards and interoperability and all of these things. So are you doing anything that's more broad and open source or towards, open standards?
I mean, we as a company we have embraced open pretty early, right? So on the software side, we are entirely open, right? I mean, we have built the software stack with PyTorch and MLIR and whatnot, right? And OpenBMC. So a lot of open tools on the software side. And then on the hardware side too, we have embraced UCIe. Obviously there's PCIe. There is all the other open standards, right? That we have embraced. Ethernet, right? So no, absolutely. I think as a company build, we are more focused on building our accelerator solutions and software. So we embrace everything around the ecosystem. We tend to be open.
And with that, thank you, Sid. And again, the website is d-matrix.ai.
Thank you, Ben. It was great chatting.